Good evening, everyone. This is Bob DeVance, K5CRX, teaching the Amateur Extra class. We'll be going through this class looking at primarily the technical aspects of the test, more so than the rules, regulations, and so forth. We're assuming that you will be able to go out and pick up those on your own and do the study that you need to do. There are many self-study classes out there, self-study courses out there, free and otherwise, that will lead you through those things as well, of course, as the books and the other things that are readily available. We will be using the RRL's material with Gordon, along with Gordon West. He has a slide deck that's prepared. We'll actually use an older slide deck and a newer slide deck because of some differences in those two, and I think they fit our purpose a little bit better on this first couple of sessions nonetheless. So with that, we'll be looking forward to working with the extra class licensing situation, and hopefully you'll be able to take the test at field day and come out as a brand new amateur extra operator. So we'll start here just in a few moments. Okay, let's get rolling for the class for tonight. This particular session is dealing with skywaves and contesting, which we might think is not that technical, since we'd said we were going to concentrate mainly on the technical subjects and aspects. But there are quite a few technical things that deal with this, things that we don't deal with every day. So I felt it was probably beneficial to go ahead and talk about doing these things that's in this first part. I do have two slide decks for this, both compliments of Gordon West and his teams. The first one is an older one. It literally just goes through all the questions on this section, talking about them all. Then it's followed up with the actual questions themselves. The newer one has the questions and the explanations integrated. So what we're going to do here actually is we're going to use the older deck first and go through all the information first. Then subsequently, we'll go back and go through the questions and answer all the questions and see if we're okay with all that. Okay, so that's kind of where we're going to try to head with all this to make it work for us tonight. And with that, I'm going to start sharing my screen and we'll get things going. So if you give me just a moment here to get my PowerPoint going and get the screen shared, and I think we will be fine. And we're going to tell it to share. And I want to share screen to share. Okay, and then. Okay, so with that, we should have a screen 2 showing there with the intro slide. And away we go, skywaves and contesting. Okay, this first slide has to do with just some good general information dealing with the ionosphere in particular. As you can see, the little chart on the right is trying to illustrate the different ionospheric layers that are around our Earth. As you can see, excuse me, looking on the right side of that, we see the D layer, the E layer, and then the F1 and F2 layers, which are separate during the daytime hours. At night, the F1 and F2 combine to become only F2, and the other two layers disappear at night, so they're no longer there at all. The idea behind all of this, it makes it great for us, is that we send a signal toward the ionosphere. It hits the ionosphere, bounces back to Earth, goes back to the ionosphere, back down again, called a hop. Can actually go from where we are here halfway around the world or more to make a contact, which makes it great, obviously for us. Also, then the effect of the sun and all the things that the sun does to us and for us can have an impact on the ionosphere and what it can and can't do, whether it reflects, whether it generates noise, or whether it absorbs signals, etc. We'll see all that happening as we go along. So this is just kind of a quick intro for that purpose. With that, let's talk about the specifics now of things that's going to be going on. Anytime we launch an HF signal into the ionosphere, it actually splits up into two different pieces, or two signals, if you please, two elliptically polarized characteristic waves, as they're called. One turns clockwise, the other turns counterclockwise, the X mode and the O mode. Key to that will be the splits. By the way, the answers are in blue. The key will be the splits into two elliptically polarized characteristic waves, meaning the O wave, ordinary, and the X wave, the counterclockwise wave. You'll see that in a question a little bit later. When we deal with satellites, often we use a circular polarization to communicate with the satellite. The reason for that is the satellites often are spinning or rotating, and the circular polarization helps us to communicate with the satellite by our signal rotating along with it, basically, and it helps a whole lot. We get a right-hand or left-hand circular. There's a whole bunch of things we can say about that, but that's really not germane to the discussion here. You can look that up if you're interested in it or want to follow it up, but it's not particularly critical here. This little chart is showing primarily right angles. That's going to be the key to a lot of things. Remember, right angles. This is showing, if you look at the top right-hand corner of this, the magnetic field and the electric field of a wave. And there are the two for each radio wave that goes out. And those two waves are in phase, but are at right angles to each other. And you'll see that right angle coming around a whole lot as we go along. Trust me on that one. The little hand that's showing there is talking about doing either a left hand or a right hand rule. There's a way that you can hold your hand and indicate which way the wave's traveling and all that. There are no questions on that, so we're not going to go into it. But if you want to pursue it, you can always look up left hand and right hand rules, and you get some graphics and some explanations on how that actually works, so you can predict what a wave is actually doing. And if you're doing some engineering stuff, that might be very handy to know. Right, quite obviously, of course. There's a good program out there for the HF frequency world called VOACAP, Voice of America program. And it actually works pretty good. It gives us the HF propagation information. You can either download it, run it locally, and it'll run on Windows or Linux, or you can just use the browser and use it online on the internet without having to install anything. They have a pretty good user manual that goes with it. Again, you can either download or you can read online and see how it works. And it's a pretty decent program. The next slide has a shot of it that you can see what it looks like in the online version. IonCap, I've not used. I don't know anything about IonCap, but I know it's there. There are no questions about IonCap. The question is about VOACAP. So this is the online version running on my computer. I told it as it drives my transmission point, I wanted Dallas, Texas, which was the closest city to where we are, where they pick the large cities, of course. And you'll notice there's a little red arrow there over the United States indicating the Dallas area. About in the center of the map, which is where it goes if we don't tell it otherwise, is the receiving point. And I can move that point to anywhere I want it to be, or I can select from different cities and so forth and get reception information, transmission information, how well we'll be able to communicate, what the propagation probabilities are, and so forth. Also, a quick note, you'll notice the day and the dark areas are the light and the dark areas. The light areas are the daylight areas. The dark areas are the nighttime areas. And the little line in between the two is called the gray line. It's gray because it's turning from daylight to dark, of course. Another slide that we have later will show that a little bit better. And there's some special things that we can do when we communicate off the gray line. We'll see that come up just a little bit later. But right now, this is just a picture to show you what the Voice of America CAP program looks like. Okay, talk about UV and hard X-rays just a little bit. These are rays that are emitted from the sun. They arrive very quickly to the Earth since they are rays, not particles. And when they do hit that, it can cause us to have a blackout on the Earth of communications. Because they're waves and they're traveling fast, the blackout generally doesn't last but an hour or so. It's not a long-term thing, as opposed to a solar flare, which can create a much longer radio blackout that happens with that. And this particular diagram they gave us, but I'm not sure what it's about. The ProLab program. I just don't know anything about it. I didn't find anything on it, but there may be something you can find if you want. There are no questions on it. That's the good part. Long path. Long path is where we communicate with the station in the longest direction as opposed to the shortest directions. For example, if I want to communicate with the station in England, the short path would be to go from here across the Atlantic Ocean over to England. The long path would be to go the opposite direction across the United States, across the Pacific and around the world back to England. That would be the long path And we can direct that if we want to. If we have a directional antenna of some sort, it doesn't have to be a fantastic antenna, but some kind of a directional antenna to send the signal in that direction, then we can actually do that. And we can communicate over the long path. Just one of those interesting tidbits that we can do with amateur radio. It's a lot of fun to do those kind of things, obviously. 20 meters has a lot of activity, and that was CW and some voice as well along the way. But key to that is the 20 and 40 meter bands are the best for long path DX communication. Long path can be found from 10 down to 160, but again, 20 meters is probably the best. Late evening, early morning hours, generally when it's available. That's goes back to the gray line thing again. Okay, gray line propagation. Next slide, wouldn't you know? Okay, gray line communications lets you communicate when you're in that gray line area with someone else who's in the gray line area. Can run 30 minutes or so, and of course the gray line is constantly moving as the Earth rotates, so the conversations would not last forever, for obvious reasons. This is the better picture of the gray line, as it were. You can see the lighter area, which is the daylight section, the darker area, which is the nighttime, and then that little sliver of the curve there represents the gray line, which will give you about 30 minutes worth of communications possibilities. Solar cycle 25, which we're in now, is doing pretty good, supposedly, at least they say it is. I'm not always sure that's true. But at any rate, you'll remember that solar cycles run in 11-year cycles. Right now, we're at the peak of the cycle, and it'll start going down before long. And the communications will get more and more sparse as that happens. One of the things that happens after sunset, if we're talking on one of the higher frequency bands, we may suddenly start to get a fade and start to lose it. The solution for that then simply is to go down to a lower band, lower frequency band, such as 20 or 40 meters, and you can continue the conversation there if you wanted to do that. Chordal hop is an interesting concept. Chord, if you remember, is an arc or a portion of a line drawn across the circumference of a circle. So a chordal hop is where our signal goes up, hits one of the ionospheric layers, and instead of bouncing back down to the Earth, it bounces across that layer, across the chord of the layer to another spot on the layer, maybe a couple of times before finally running out of space and coming back down to Earth again many miles away. The great part about that is it doesn't go to the ground, so it gives you a stronger signal along the way. Chordal hops always occur along the dark path opposite the sun, that is in darkness. And you'll see some reference to that a little bit later on. One of the great things about it is you don't have the loss that you have with a normal skip, where the signal goes up and down between the ionosphere and the Earth. Since it's staying in the ionosphere and then coming back down to Earth, you have a lot less loss, which is, that's relatively obvious, I guess, isn't it? Okay, another picture of that, just to kind of illustrate this whole thing. If our signal went up there on the right side up to where it says F1 layer at 90 to 150 miles, and then the signal bounced across rather than coming back down to the Earth, it could bounce around that layer and finally come down on the other side of the world. That would be a chordal hop. Chordal hop propagation can result in some very loud signals, but especially on 80 meters. There's no ground reflection, which makes them stronger. There's a website there. I've not verified that website. If you want to try to check that out, it's a website that deals with that very specifically. Some good friend named Chip is getting ready to see if he can do a chordal hop on 10 meters. We wish him well, of course. Another thing we can do is called transequatorial propagation. Well, that's a mouthful, isn't it? It has to do with the magnetic equator of the Earth and an equidistance on either side of that equator to two stations which want to talk to each other. For us here in Texas, we're far enough away from the equator that that's not generally a real good thing for us to do. It doesn't work well for us. And in some ways, it says at the bottom of Alaska, it's not going to happen. But at any rate, we'll cover the principles. It gives a path of about 2,000 to 3,000 miles perpendicular. There's that right angle again, perpendicular to the magnetic equator. Don't know a lot about it, just know that it works. Total distance of a contact could be about 5,000 miles. That is about 2,500 miles on either side of the equator is what we're saying with that. Essentially, the signal goes up, hits the F2 layer, and comes back down again 5,000 miles away, 2,500 miles between the equator and each station. Best time of day, mid-afternoon, early evening. That gives the sun time to condition the ionosphere, get everything ready. And then by that time, by the mid-afternoon, the early evening, everything is prepped, warmed up, if you please, and it works better during that period of time for trans-equatorial propagation. Okay, steady path of UV radiation is good for the ionosphere, but being blasted with hard X-rays and charged particles from solar flares is not a good thing. During such an event, absorption and the delayer can be almost total. That means the signal goes up, but nothing comes back down. In addition, big globs of fast-moving charged particles tend to wrinkle the ionosphere. That means it's going to travel more slowly than the X-rays or the actual rays or radio waves that would come from the sun toward us. An increase in noise results as these particles, primarily the delayer, recombine and just generate a lot of noise, plain and simple. So solar flares is not good. It generates a lot of noise. The A and K indices are some measures that we use to indicate how well propagation is going to occur. As we look at the geomagnetic fields that interfere, that correspond rather between the Earth and the sun. We use magnetometers to measure those things, very sensitive instruments that do that. They're published in a number of places. The ARRL publishes that information almost daily, or maybe it is daily, come to think about it. And there are a couple of other places we'll refer to in just a moment where you can get that same information. As these things rise, these indices rise, they're telling that there's an increasing disruption in the geomagnetic field, which may or may not be a good thing. Okay, Earth's magnetic fields are concentrated near the magnetic poles, that is, North Pole and the South Pole, as you would expect. Magnetic disruptions can also be concentrated in these regions, of course. In the auroral region, that is, that region around the North or the South Pole, there's an oval region there where those auroras occur that are kind of interesting. They are absorptive if you're under them, basically. If you send a signal up from Alaska while the aurora is going, it'll go up and just be absorbed. It won't go anywhere. If we're not there, though, we can actually bounce signals off of the aurora, which is a whole other discussion from another slide we'll get to here in just a moment. Okay, and absorption is normal in the polar regions. Interplanetary magnetic fields, again, talking about this some more. The Earth and the Sun, of course, each have north and south poles. You'll remember from your days of high school science, you take two magnets and you put the north and south poles together, and there's an attraction there between the two. The same is essentially true between the Sun and the Earth. We use the thing called the B sub Z figure. B being the magnetic fields and Z being the orientation of the field, normally the vertical orientation of it. We'll see a little bit more about that in just a minute, though we won't go into it in any great detail. Interplanetary magnetic field contributes to the character of the Earth's ionosphere. The Earth will have the greatest interaction with the magnetic field from the Sun when the field is oriented north to south, or as they express it on the exam, southward. Just remember, the key there is southward. Okay. Okay, X extreme. X-class solar flares are very, very disruptive. They emit large quantities of charged particles. With particles, meaning they get to the Earth a little bit slower than the waves would. A lot of X-rays can come along with that, of course, which travels pretty fast. X-rays can certainly create a lot of ionization, wreak havoc with the ionosphere, not necessarily the way we want it to, however. And a good thing the solar flares don't last forever. That is, the X-class solar flare is very disruptive, but they don't last very long at all. Okay, this is a very intense little slide, this and the next slide, but there's two key things for these two slides. The first on this slide is this. WWV and WWVH are radio stations that belong to NOAA, the National Oceanic Atmospheric Administration. WWV and WWVH broadcast on 2.5, 5, 10, and 15 megahertz continuously. The WWV station is in Fort Collins, Colorado. WWVH is in Hawaii, but they send about almost the same thing, but not quite in the same order. They're on the same frequencies, however. It depends on how well you can receive either one during any particular time of the day. You pick the frequency on which you can receive them. But the point for this slide, though, is to say that they broadcast a lot of the geophysical information on those two systems. WWV at 45 minutes after, WWVH. Let's see. No, I'm sorry, I got it backward. WWV is 18 minutes after the hour. WWVH is 45 minutes after the hour. So it's a good place to get information on A and K and a bunch of the other information that's going on in the ionosphere that affect radio communications. In this slide, the key thing to remember about is the lower left corner, the extreme G5. A storm level that's extreme, it's G5, is very rough on us, very hard on us, very hard to communicate when that's happening. There is a website that's mentioned there where you can look at some of those things and get some explanations of what the different scales mean, what they're reading, how they're measured, how they're derived at, and how often they're publicized. Reverse radio beacon is a nice service where we can send out a signal and see how well we're being received. If in fact we are being received, of course, that's called the Whisper WSPR, WhisperNet. There's several others, but Whisper is probably the premier one. That website at the bottom, I have verified that does work, and it will tell you what it's hearing out there. Normally, those signals are sent as either CW or digital signals, and then you can see if you're being heard or not there. Okay, and this is a screenshot from their website. And you see some hops that are going back and forth on that. You can select just about anything you want. You can select the band, you can select the mode, you can select a lot of different things and find out how the signals are traveling back and forth. The propagation on the Earth is connected to what's happening in the sun. I think we've said that in 3 different directions already, of course. A G5 report tells us there's a geomagnetic disturbance, an intensity of 5 on a scale of 1 to 5, which means it's pretty severe. A couple of websites there that are also related to that, if you'd like to take a screenshot of that or remember that. UV transmissions are a good indication of sunspot activity, of course. Primary ingredient necessary for the normal ionosphere to form and to function. And then this is kind of a weird one for the test. It's one of those I think we just have to memorize. At least for me, that's true. I don't deal with angstroms every day. Angstroms are a measure of wavelengths in the light frequency. So a 304A solar parameter measures UV emissions at 304 angstroms. That's the answer to the question, to the test. That's the answer to the question on the test. And there again is a website there. I've not checked that website out to be sure that that's accurate. Sporadic E, as the name implies, sporadic means it can come and go. Sporadic E are things that bounce off the E layer. Often these will be, you'll see these on 6 meters. We call 6 meters the magic band because these things will come and go like that. You'll have a conversation running and boom, it's gone. And it'll pop up and boom, it's gone again. You just never know. With sporadic E. Generally, sun up, sundown, because the E region is going to disappear at night. It can be just a few minutes, or it can be several times, depending on the frequency that you're working. Sporadic E is sporadic, as we said. Best times for it to occur, winter solstice, or in the dead of summer. Mainly summer is going to be the key to that one. Sporadic E in the summer. Another chart showing things going up and down to the ionosphere. The first one on the left, 7 megahertz bouncing off the D layer, 14 megahertz bouncing off the E layer, a 21 megahertz bouncing off the F1, and a 28 megahertz bouncing off the F2 layer. Just illustrative of signals bouncing. Now, they can also bounce up and down depending on what they are and the time of day and a whole host of other kinds of things there. Of course, as we said, the E and the D layers do not exist at night for us. Those two disappear. And F1 and F2 combine into F2 for us at night. Generally speaking, the higher, that is the VHF and UHF frequencies, would go straight on out. They don't generally get refracted. They can, depending on the sporadic E again and what it's doing to us. Within the E layer of the ionosphere, the 6 and the 2 meter excitement is there. Meteor scatter also takes place with this. Meteor scatter is a whole nother thing, if you please. Meteor on E, if you want to remember it that way. This is just a statement from Gordo, who said he had made some contacts when there was a meteor going on. As we see that as the meteor is coming into the Earth's atmosphere, it has a tail on it. We can actually bounce signals off that tail and can actually carry on short conversations. 28 to 148 megahertz are the best frequencies on to hear the things on meteor scatter. 28 to 148 is the key answer there. Of course, in computers, we tie our computers to our radios. A lot of things go on these days. A lot of the radios have sound cards built in and can just connect to the computer, and you can run with it very, very quickly. However, for meteor scatter, there's something specific. MSK 144 is the mode that is used for that. It's a special mode just for that. MSK means minimum shift keying. There's a little explanation there if you'd like to look at that. The key to this is you use MSK 144 for meteor scatter contacts. Okay, FT8 and FT4 are normally modes that we communicate very quickly on, and that is very, very briefly, I guess is the right word. We don't send a lot of information. That is, we don't carry on conversations. Like in PSK 31, we can actually transmit back and forth and say, I'm running on this kind of rig, I have this kind of antenna, whatever the weather here is, stormy, or whatever it is. You don't do that with FT4 and FT8. It's strictly a very brief communication back and forth. Standard practice on VHF and UHF on FT4, FT8. To use your grid square with that instead of a signal to noise report. Okay, auroras. Again, we're talking about dealing with magnetic storms and auroras. In the interior Alaska, there's an active aurora. Best thing you can do is go outside and enjoy it. Look at it, because you won't go anywhere with a radio signal if you're right under it. But if you're elsewhere, you may be able to bounce the signal off of it at VHF or UHF frequencies, even, all depending. Beautiful picture of an aurora. Okay, auroral contacts generally will be on CW. You may not hear a tone, you may not hear anything, but just kind of a shh kind of noise thing in burst. It's somewhat similar to the old days of spark gap transmitters, where you just got bursts of noise that represent dots and dashes. Beautiful picture of solar flares. A little chart there that it can be used supposedly for figuring out how far you can go from a transmitter. And I believe this has primarily VHF, UHF in mind. But if you see on the left, you have the amount of power you're putting out. And on the right, how high your antenna is, and where that line you draw between those 2 point crosses. The middle line gives you the range, as it's showing there. If you're transmitting 1 watt and you have a 10-foot high antenna, you would expect to get a range of a little less than 2 miles. Likewise, 6 watts at 10 feet, you would get a little bit further than that. 25 watts and a 10-foot antenna would take you up there about 3.5 miles. According to that chart. Unfortunately, they didn't provide a lot of information on why this chart was included. If you want to try to compute the distance that your VHF signal is going to travel, you can use this formula. The distance in miles is equal to 1.415 times the square root of 2 times the height of the antenna in feet, and that will give you the distance in miles. Now, normally VHF, UHF signals travel line of sight straight out. However, if they go to the horizon, they will tend to bend around the horizon just ever so slightly, called a range enhancement as they go around the geometric horizon. Generally about a 15% increase over the straight line distance when you're going around using the geometric horizon as our measure of how far a signal is going to go. Okay, electromagnetic components of electromagnetic waves are perpendicular or orthogonal. Orthogonal means right angles. There's the right angles again, if you please. Perpendicular, of course, means right angle as well. Direction of wave propagation is orthogonal, right angle to the magnetic and the electric fields. All 3 components known as mutually right angle or orthogonal. Okay. Ducting is another interesting thing that happens. In ducting, normally the atmospheric conditions are just right so that a signal that would normally not go very far may go for a couple hundred miles. I've seen this happen with VHF on repeaters, where a repeater out in mid-Texas would come in here just like gangbusters, be there for a little while and then disappear. called ducting. Generally, that ducting would occur over a large body of water or a large body of desert. Now, I don't know if they consider Texas all desert for that to happen or not, but a large body of water, of course, is the answer on the test that we're looking for ducting to work. In free space, a radio wave, travels at the speed of light, which is normal. In air, about the same for all intents and purposes. But when we run the radio wave through something else, through a coax, through a ladder line, to an antenna, etc., or some other medium, then it will slow down. That's called the refraction index, or index of refraction, which is inversely proportional to velocity factor, which you'll probably find more familiar. When we deal with coax, we often talk about the velocity factor of a coax as, for example, 0.75. Which means that the radio wave travels through that coax at the speed of light times 0.75. That is 3/4 the speed of light. Anyway, inversely proportional index of refraction to velocity factor. Troposcatter. Tropopropagation is a whole other thing. We go into the troposphere, which is a little bit lower than the D layer, and it's normally very short communications. Normally the antennas for troposcatter or tropo go almost vertical. They hit that, come back down, and scatter all over the place, and then various stations within 100 to 300 miles can pick up those signals. We use that in Alaska for some of our communications information because it just worked, and it worked well. Troposcatter propagation, typically 100 to 300 miles, occasionally further, but that's typical, 100 to 300. And we're back to the right-hand, left-hand rule again. We can look at all these different things, the phases and the lengths and the directions, and use a right-hand rule. That's another one for the left-hand rule. Right-hand rule is the answer you're looking for. We're not going to talk about it beyond that. If you really want to get into it, it gets pretty deep, and you can find that online very easily, and a lot of good pictures of it, how it's used, and why it's important for engineering. Vertical polarization is when our antenna is vertical. Obviously, it generates a vertically polarized signal. If we take our beam antenna, turn it on its side, then it would generate a horizontally polarized signal. And we use the horizontally polarized signal, for example, on 2-meter FM. That's the convention. So if your antenna is sitting vertical and you're trying to communicate on 2-meter FM, you don't get a very good reaction from that. It's quite actually 20 dB loss, just automatic happens. Vertical polarization assists and is good for ground wave communications. Ground wave communications are normally very short range communications compared to radio waves that bounce off the ionosphere, of course. And they're showing a picture here of it for two vehicles, both with vertical antennas, following the ground wave actually going across the top of a mountain, which can happen. So key there, vertical polarization for ground wave. Anytime you make a contact, you use your full call sign, period. That's just it. That's the standard rule on anything you do, pretty much. Split operation. This is a cool answer. Split operation reduces interference, separates calling stations from the DX station, lets the DX station stay in the clear and out of the U.S. phone band. What's that saying? That's all of the above. That's what that is. Normally, if we're working a de-expedition station someplace, that station will often transmit on one frequency and say, we're listening up 10, we're listening down 10. Usually it's up 10, it can be down 10, meaning they're transmitting on one frequency that keeps that frequency clear so nobody else is transmitting on it but them. And then they're listening for the pileup 10 kilohertz above that. So that keeps the two separate, makes it a little bit easier for them to control the pileups that they're invariably going to be dealing with. So most all radios will have a dual VFO, a VFO-A, variable frequency oscillator, A and a B. You set one to one frequency, one to the other, and you transmit 10 kilohertz above the receiving frequency you're receiving. Anyway, all three of those answers are correct. All of the above. There are a lot of logging programs especially for contests, but for anything else for that matter. It mentions N1MM, which I have, and there's half a dozen others. I forget the one that the Amateur Radio Club has. We have one that we have a license to, but most of these will generate a Cabrillo formatted log file, which is used to submit the contacts to the contest host. It's just a standard file format called Cabrillo. The ADIF format is another one that's used, the amateur data interchange format. And most all logging programs will export their data in ADIF or in Caprio. And there are programs separate that you can download that will convert these back and forth as well. And there's some hosts that will take either one, either Cabrillo or ADIF, and they'll take care of whatever conversion they may need. Good, safe thing to do if you're going to submit a log for a contest, for your contacts in a contest. Check with the contest host first and see what they like to have, and then send them what they want. They may want an Excel spreadsheet. You just never know. Okay. In VHF UHF contest, we generally will have a calling frequency that we're using. We make our initial contact on the calling frequency, then move either above or below that frequency to carry on the conversation. That's essentially what this is saying here. Most of the weak signal single sideband activity is found on either side of the calling frequency during that particular contest, because we're not talking on the calling frequency, we're just establishing the contest there and then moving either up or down as is appropriate. No contesting on 30-meter band, period. End of discussion. About all you really need to know about that one. Okay, DX is an interesting thing that we do. We like to collect QSL cards that prove we've been there, we made that contact, if you please. There are usually QSL managers that manage these things for the DXpeditions, but we've moved up a lot in the new world now. We use the Logbook of the World a lot, and there's a couple others out there as well that people use. The Logbook of the World is probably the premier. It's hosted by the American Radio Relay League, and you put your information in there. If the other person on the other end puts their information in there, then it will automatically correlate the two and confirm the contact between the two of you, which is pretty handy for doing that. Picture of some cards just so that you'll have it. And with that, we're going to stop there. And then in the next session, we'll actually go through the questions, review all the information, and give you all the answers to all the questions. Look forward to the next time.